Welcome students to the EPG Pathshala. Today we will learn best practices of solid waste, its different case studies, national councils and policy, solid waste management and planning under the paper solid and hazardous waste. So, our different objectives include first to know what is solid waste management, second learn about different waste to energy conversion processes, third to understand the importance of solid waste management through different case studies, and fourth to know about policy framework in India. So, now starting with the introduction. Earlier, solid waste management practices intend simply to eradicate waste from the surrounding area so as to maintain a good public hygiene. But after recognizing the risk of uncontrolled disposal on human health, steps were taken and implemented mainly through sanitary landfills. Recently, many techniques and waste to energy technologies have been included in managing waste. Globally, efforts are made in order to reorient solid waste management techniques towards sustainability. Asian countries including India are actively involved in orienting themselves towards integrated solid waste management techniques. Though the amount of attention paid towards solid waste management techniques varies from country to country and is directly related with their economic status. Therefore, it is necessary to inspect the condition and nature of solid waste generation and then adopt a plan accordingly in order to properly manage escalating amount of solid waste. It is therefore necessary to formulate a proper strategy depending on nature and amount of solid waste generated. Solid waste management. Asia is distinguished for its diversified culture, climate, economy, food habits and topography. This is reflected in their waste generation. Best practices for solid waste management is gaining due importance these days because of increasing population, legal intervention worldwide, evolving of new technologies as well as rising public awareness regarding health and hygiene. Now, opportunities for energy conversion. Rapid urbanization, globalization and economic expansion are creating pressure on every sector, be it food, fuel or energy, which in turn increases the cost of energy, and the impending shortage of fuel becomes a more alarming issue. Due to the existing pressure on biomass reserve and the rising fossil fuel prices, generation of energy from solid waste is gaining importance as an alternative source of energy. Therefore, in current years, there is an increased interest in treating waste as a valuable resources rather than as a trash, because fertilizers plus energy can be obtained from it. Research and development around new energy source from solid waste is attaining great importance these days. Now, transformation of organic waste into fuel gas through biochemical and thermochemical treatment is also being explored. These technologies are in preliminary stages of development and further technological evolution is needed for converting waste to energy. Currently, biological and thermal processes are frequently used to convert municipal solid waste into energy. Now, depending on the type, quantity and physico-chemical characteristics of waste, different techniques like direct combustion, gasification, biomethanation, refuse derived fuel RDF is adopted to produce energy from waste. In India, various projects are underway to alter waste to energy. Now, first is thermal conversion. Under thermal conversion, we will first see incineration. Incineration is most basic waste handling method that have been used in different parts of the world due to its ability to reduce waste mass by 70% and waste volume by 90%. But incinerators release air pollutants such as sulfur dioxide, NOx, carbon dioxide, carbon monoxide, heavy metals, dioxins and toxic fly ash, which are proven health hazard. These air pollutants have the capability to penetrate the atmosphere and may make the environment toxic. Now, to control air pollution, incinerators have to be well equipped with air pollution control devices. The incineration process is conducted at a temperature dimension of 750 to 1000 degrees Celsius together with steam and electricity generation. At the end, an ash known as incinerator bottom ash IBA is produced that should be reused appropriately as it is generally contaminated with heavy metals such as copper, lead, manganese, zinc, etc. Now, we will see first case study. In India, the first incineration plant was installed in 1987 at Timarpur, New Delhi. The unit operated at an initial capital cost of 20 crores. Was proposed to incinerate a maximum of about 300 tons of municipal solid waste per day to produce 3.75 megawatt of electricity. The plant could not run beyond its 21-day trial period and failed because of bad conditions of waste supplied. A net calorific value of at least 1400 kilocalorie per kg was required to run the plant, while the incoming waste, which was supplied in the range of 600 to 700 kilocalorie per kg. Next we will see pyrolysis. Pyrolysis is thermochemical disintegration of organic waste in oxygen free environment. Pyrolysis works extremely well with organic waste of high heat value. During the pyrolysis process, the hydrocarbon present in the waste react at temperature around 450 to 500 degrees Celsius in an oxygen free environment. The end products generated are pyrolysis gas, pyrolysis coke, char, which is mixture of fixed carbon and ashes, and tar, which is condensable gas. The accepted equation for pyrolysis is given below. Now, fuel gas produced during pyrolysis consists mainly of carbon monoxide and hydrogen, which are suitable either for electricity generation or for heat production. The flue gas has a calorific value in the range of 22 megajoule per meter cube to 30 megajoule per meter cube. This is also dependent on the kind of waste material that is being processed. Depending on their working parameters, pyrolysis is of three main kinds, namely conventional pyrolysis, fast pyrolysis and flash pyrolysis. Conventional pyrolysis is time consuming process that operates under slow heating temperature of around 550 to 900 degrees Celsius, creating solid, liquid and gaseous end products. It is employed primarily for producing charcoal. Now, fast pyrolysis is related with tar generation and drives at temperature around 850 degrees Celsius to 1250 degrees Celsius, while flash pyrolysis work at temperature around 1050 degrees Celsius to 1300 degrees Celsius. Fast or flash pyrolysis technology, which requires a high temperature range and has a short residence time, is widely accepted nowadays. Now, we will see second case study. Lately, Tamil Nadu has set up a pyrolysis plant of 10 TPD capacity and is operating successfully in Coimbatore. Likewise, other 10 TPD plants have achieved success in Masaipet in Andhra Pradesh and Nawapur in Maharashtra, Madhya Pradesh, Mathura in Uttar Pradesh, Patna in Bihar. Now, and 5 TPD plants have been installed in Bichiwada in Rajasthan, Durg in Chhattisgarh and Nagpur in Maharashtra. Now, we will see gasification. In gasification, carbonaceous materials including waste and biomass get partially combusted into useful, convenient gaseous fuel or chemical feedstock. The process of gasification utilizes very little to no oxygen as contradicted to combustion or burning associated with incineration. During gasification process, the product gases like carbon dioxide and water are reduced to carbon monoxide, along with hydrogen. The process may also generate some amount of methane and hydrocarbons and various other toxins like tar, small char particles and ash. The gasification agent utilized in the method allows the feedstock to get effortlessly altered into gas by the assistance of diverse heterogenic reactions. Gasification based system make it promising to achieve high power generation and efficiency, which cause carbon dioxide to get generated in intense form, plus it is easier and cheaper to capture and sequester it, thereby preventing it from reaching the atmosphere. Now, case study 3. There are number of gasification plants of various power capacities operating in India, such as 150 kilowatt capacity plant installed by Evergreen at Beri, Tumkur in Karnataka, and the West Bengal Renewable Energy Development Agency installed by Synergy. A 415 kilowatt power capacity plant was installed in Jammu at Hindustan Pencils by BTEL. A 500 kilowatt plant was installed at Betmangala, Karnataka by Evergreen as well. At Arashi and Gomati in Tamil Nadu, a 1 megawatt power capacity plant is running successfully. Now, refuse derived fuel or pelletization. Refuse derived fuel is an effective method of altering waste into energy. Alteration of municipal solid waste to RDF entails different steps such as drying, separation of combustibles, size reduction and pelletization. After compilation, municipal solid waste is heated to eliminate around 30% to 60% moisture content so that the pellets have reasonable heating value. The waste is dried by spreading in an open yard and allowing it to sun dry. A sun drying continues for 1 to 2 days depending on the moisture available in the waste along with the climate of the region. Now, after drying, the waste is passed via screen for removing sand and grit. Thereafter, it is passed to a separator in which the light combustibles and dense fractions are separated over an air barrier. Magnetic separators are employed to remove all ferrous particles, which are then grounded to 20 to 25 mm particle size. This feed, which may be made of celluloses, calcium hydroxide, cement kiln, dust, free lime, fly ash, etc., is sent to pelletizer for densification with around 5 to 10% bin so as to enhance calorific value of the waste. Now, fourth case study. In Chandigarh, India, an RDF plant has been set up to treat municipal solid waste into fuel. Operators estimated that 350 TPD of municipal solid waste were accessible for dispensation by the plant, and it is expected to treat waste up to 500 TPD in the coming years. However, presently the plant is not in working condition. Finding suitable uses for RDF continues to be a challenge. Now, biochemical conversion. Under biochemical conversion, first is anaerobic digestion. It is biochemical process which is accomplished in an oxygen free environment where microorganisms act on the organic feedstock, liberating biogas and lessening the quantity of waste in the process. The biogas thus produced can be employed as combined heat and power or may be used as fuel. During the decomposition process, the temperature initially rise as high as 65 degrees Celsius and then begin to fall gradually over a couple of months. At the end of the process, methane gas is produced, which possesses high heat value and can furthermore be converted to methanol. During this process, valuable commodities like biogas and digestate that can be employed as organic amendment such as soil conditioner can be generated and is feasible devoid of any oxygen supply. Now, fifth case study. In India, Gujarat is the only state which is successfully running waste to energy plant through anaerobic digestion. MS Kanodia Chemicals Limited in Ankaleshwar generates 2 megawatt of power using this treatment. Similarly, Maharashtra is also taking the initiative to utilize waste and convert it into energy by installing many pilot projects at Mumbai, Pune, Nasik among other places. The Ministry of New and Renewable Energy MNRE has given subsidies to 3 demonstration projects at Hyderabad which consist of 6.6 megawatt, Vijayawada consisting of 6 megawatt and 5 megawatt in Lucknow. However, these projects were not successful in turning waste to energy. Now, we will see vermicomposting and composting. Composting is organic breakdown of biodegradable organic waste by bacteria, microorganisms or earthworms under aerobic condition to a situation which is sufficiently constant for order and pathogen free storage and safe for use as biofertilizers in agriculture according to United Nations 1993. It has been evaluated and proven that compost and vermicompost from waste is very effective in soil remediation and increases the nutrient availability in soil, aids in plant growth and ultimately increases the plant yield. Now, case study number 6. In India, under the National Scheme of Solid Waste Disposal 1975 to 1980, cities with population of more than 3 lakhs were installed with 10 operational composting plants which had composting capacity to treat 150 to 300 tons of municipal solid waste per day according to Government of India 1995. Currently, low waste quality, incorrect selection of apparatus, poor safeguarding, soaring production cost, financial failures and poor marketing efforts are some of the key challenges that the composting procedure has to overcome, so it could be able to successfully implement on large scale. Now, we will study policy and legislative frameworks in India. The primary responsibility of management and disposal of solid waste is of municipal authorities. In the year 1969 to 1974, the 4th 5-year plan declared by the Government of India commenced attempts to set better facilities for disposal of solid waste by giving loans and grants for setting up of vermicomposting and composting facilities. Government of India assigned a committee to assess the crisis of solid waste management in India. 76 suggestions were made by this committee that covered 8 areas of waste management. Local acts and state legislation that administer municipal authorities are provisions to collect, transport and dispose solid waste. This responsibility is assigned to Chief Executive of Municipal Authority. In most of the state, the legislation does not cover important organizational or technical details of proper solid waste management. Laws cover the sweeping of streets, putting community bins, transporting waste to disposal site and finally the treatment of waste, but they do not give the details that how this has to be done. Moreover, law do not specify which responsibility to be assigned to a citizen and which to municipal authorities. Additionally, they do not specify collection system, appropriate waste storage depots and do not mention waste treatment facilities. Therefore, most of the state legislation except Kerala does not fulfill the efficient solid waste management facilities. Now, in the year 1990, Ministry of Environment, Forest and Climate constituted NWMC, National Waste Management Council, with management of municipal solid waste as one of its objectives. It recommended 22 municipalities to estimate the quantity of solid waste and its transportation and disposal. In 1993, National Plastic Waste Management Task Force was constituted by NWMC to reduce the health impact and undesirable environmental problems arising out of plastics. Based on the suggestion, in the year 1998, MOEFCC drafted recycled plastic usage rules. which puts a ban on carrying, storing and packing of food articles in plastic bags and specified standards for making plastic bags. According to Municipal Solid Waste Rules 2000, local municipal bodies are accountable for implementing these rules and provisions for collecting, storing, segregating and disposing of solid waste. These rules direct that appropriate technologies like composting, vermicomposting, anaerobic digestion, pelletization must be adopted for organic fraction of waste, while for inorganic fraction of waste, incineration or landfilling must be adopted. In the year 2000, a manual by CPHEEO, Central Public Health Environment Engineering Organization, was published on managing municipal solid waste for guiding urban local bodies ULBs under Ministry of Urban Development. Several other acts and rules have been formulated to deal with solid waste management. Under these rules, it was made mandatory that all cities to develop waste processing and treatment technologies by 2003. As per the manual, waste management plan should cover short-term 5-year plan and 20 to 25 years long-term plans. The short-term plans should be split into various action plans that must cover different aspects related to waste management, like initiatives for waste minimization, community participation, institutional strengthening, waste collection, transportation, treatment and other policy changes if required. Presently, MOEF and CC has revised the Municipal Solid Waste Management and Handling Rules 2000. The revised rules was socialized in 2013 and then again in 2016 and is concluded as Solid Waste Management Rules 2016. Likewise, new e-waste rules, plastic waste rules, fly ash and biomedical waste management rules were under revision and was promulgated in 2016. Swachh Bharat Mission. The most important declaration for development of India by NDA government is that by the year 2019, India will be open defecation free. Ministry of Urban Development MOUD, Government of India took this foremost initiative. It was initiated on 2nd October 2014, the birth anniversary of Mahatma Gandhi. It is a national campaign that covers 4,041 towns to clean streets, roads and rail networks of the country. SWM is the major element of this mission. Government of India has allotted rupees 14,623 crore for Swachh Bharat Mission for urban areas, out of which 7,366 crore is allotted for 5 years, that is from 2014 to 2019. Now, to summarize this module, we have familiarized about best practices involved in solid waste management, energy recovery from solid waste, biological conversion of solid waste and national policies of solid waste management. That is it. Thank you.